Next up, we have Ian Deane, a Unity game developer. He's got a Bachelor of Science in Physics from the University of Victoria, and he's a passionate developer of physics-based video games. And in fact, what he's going to be presenting about this time is what he calls the Ministry of Silly Walks presents physically simulated walking. So it's a physical simulation of like actually walking, and it's going to be a terrific presentation. And hopefully we'll just hop right to it.
Yes, absolutely. And without further ado, let's give Ian Deane the floor.
Hello, everybody. My name is Ian Deane. I am a game developer. I've been working in games for about 10 years. I mostly work on Unity Asset Store assets, but I've also done work on other people's games, and I work on my own games. Today, I'll be talking about physically simulated walking, which is a project that I've been working on for a couple of years. You can see some of the results on this page. There's some obviously funny results, but in the bottom is the current state of a character, which is actually getting to be fairly usable. So I'm going to be talking about that today. So a physically simulated character is, here I have an example of one. It consists of body parts that are separate rigid bodies constrained together with joints. The joints are driven by motors. In my case, there's 19 rigid bodies in each active Ragdoll character, and the characters have 44 degrees of freedom. So inspirations for my project are, I just find physics games fun. I feel that realistic physics gives games an extra level of immersion. And there's often awkwardness and emergent behavior that comes with physics games. There's a lot of humor that comes out of physics. So plus I'm a physicist by training. So I've always loved physics, and these are the sorts of games that I'm hoping to be able to create once I get this working. So let's talk about previous work that has been done on physically simulated characters. So in 2010, there was this project, which it just doesn't use machine learning. It uses math to control a character. Then in 2017, Google DeepMind created this guy. This is a physically simulated character that doesn't use animations. It just tries to get from A to B. And they just wanted to prove that it was possible to teach something to walk. This is Ubisoft 2019. They're working on a physically simulated character. There's a Korean group that's done some work on physically simulated characters. And my work is based on the next one, which is Deep Mimic, which essentially uses reference animations to train a physically simulated character. All of these, there's academic white papers for, so you can look them up and find out exactly how they did these things. Now, I caution you a bit with these academic results. They often look great, but there's often things about them that make it awkward to use these in a real game. For example, they'll sometimes require a high fixed update rate, or the models will be very large and hard to sample. Sometimes the results are fragile. They look great starting from a particular start pose, but if you're in a real game, if your character is in a different pose, the neural net might not know what to do. So yeah, often your results may not be as good. So I've been working on this for a couple of years now, and this is the state of where things are at. There's 4 main skills that my character has. It can walk, it can jump, it can tumble. So if it's moving and it falls down, it can do a somersault and get back to its feet. And it can get up both prone and supine. Then there's the video showing what it can, all these put together, and this is a recent clip showing it running on a ball. So that's where things are currently at. The character's reasonably usable. How it works. So some actions are controlled using machine learning models, and some actions are mimicked canned animations. So here I've got an example of a giant troll character. He's walking, which is controlled using machine learning, and the throw is layered on top using this reference rig. The transparent rig is a classically animated rig, and it's doing a throw motion, which is being copied by this other rig. So this is another example of where I'm using a canned animation, which is for idle. I tried to train idle, but it always creeped and fidgeted. So this idle, when it's walking around, it's actually using the machine learning. But when it pauses, like right here, he's using not machine learning. I'm just using some physics joints to strap his feet to the ground and another joint to help him keep his balance. So let me talk a little bit about what machine learning is and how it works and what these models are. So I mentioned model, which sometimes are called neural nets. So essentially, they're a giant matrix of numbers. They're organized a special way. So there's nodes organized into layers, and the layers are connected by connections. These are kind of inspired by animal brains. The nodes are neurons, and the connections would be dendrites. The connections all have a weight associated with them. And essentially, to use one of these, you feed in numbers between 1 and 0 as the input. These get multiplied by the weights, and that produces the input for the next layer, which get multiplied by the weights, and that eventually out the bottom, you generate the output. I'm just going to pause for a moment just to check the Discord to make sure that everything looks like it's working. I haven't received any statement that it's not working, so I'm just going to keep going. So I'm on this slide, view present. Okay, so that's roughly how a model works. Then and then the output is the last layer of nodes, which are also numbers between 0 and 1. These weights get tuned through a learning process. So the neural network sees the world like this. It doesn't actually know anything about what it's being asked to do. It sees the inputs that are just a bunch of dials, and then its outputs are a bunch of knobs it is allowed to twist, and then it's given a reward for its behavior. And in the training process, it learns how to twist these knobs for a given set of inputs in order to generate the greatest reward. So in my case, what are my inputs? My inputs are observations that describe the state of the limbs and the world. This is essentially a long array of numbers that are between -1 and 1. So rotations, I'm encoding just as the terms of a quaternion. They'll be inputted as 4 different numbers, or a single float for hinged joints. The rotations and positions have been put into base frame. So if you picture yourself as the neural network, you don't want to put in world space rotations because it's hard to know if the character's in the same pose or not. So you want these rotations standardized in some way. So I create a coordinate frame. The pivot is at the player's feet, and when the player is going forward, or it's aligned so that the gravity is up, and player's torso forward is forward. And most of the observations are in that frame, but I also use other frames like the hips, the parent rigid bodies in some cases. So I'm passing in about 250 float values to my models. I'm passing in positions and rotations twice. Once in hit frame. So this is independent of how the character, these observations are independent of how the character is positioned or rotated in the world. They essentially give pose information so that the model knows what pose the character is in. I'm also passing in for the feet, hands, head, and hips, where these are in the base frame. And this gives the model information about how it fits into the world. I pass in ground context, ground normals, height from the ground for various body parts like the hands and the hips. I also have a measure for how long I've been holding a pose. This is important because the model has no understanding. It just has its inputs. It doesn't have a memory of what has happened in the past. So some of the animations, they have a pause in them, but it needs to know how long it's been paused for so that it knows when it should start moving again. I also pass in the goals, which are desired heading, desired velocity, and desired angular velocity. The heading is the only thing that's actually in world coordinates. Everything else is in base frame. And then I pass in the center of the mass for the whole system of rigid bodies, heading, velocity, and angular velocity. And so the neural net can compare these to know how well it's doing at meeting the goals. For slope, I'm using a ground measurement with like 3 raycasts. For a little bit, I experimented using visual observation. Beautiful thing about neural nets is they can interpret visual observations. So here I've actually got a depth texture, and the green blobs are where its feet are going. And that worked fairly well, but it took a long time to train, was complicated, and the results weren't much better than the slope normal. So for the most part, I'm using the slope normal because it's just so easy and quick. Okay, so my outputs are just another big array of numbers between -1 and 1. These represent the target rotation for each limb. I encode these as a 4-field angle axis representation. The axis is normalized, and then the 4th field is the angle about the axis, and then I convert that to a quaternion and assign it to the joint motor as the target. Targets, I also return the target strength for each joint, and I am cheating a little bit. I include a magic force and a magic torque that's applied to the character's hips. It helps the character keep its balance and keep itself out of trouble. This is really important for the get up, which I want to be extremely quick and reliable. So the magic force for the get up is almost strong enough to lift the character and align it upright, regardless of what position it's in. One advantage of using, some projects have used torques and forces instead of target rotations. I like target rotations because it makes it easy to mix different actions together. That's harder to do if your output from your neural network is torques and forces. And work has been done that shows that it produces good results either way. My models are sampled 20 times per second, and I interpolate the in-between frames. About my model size. Originally, I started with 3-layer networks with 512 nodes. These networks took 4 milliseconds to sample. Jumped a frame there. 4 milliseconds to sample, which is pretty long. That's about a quarter of the total CPU time available for a frame. So you can really only have one character in a scene with those big models. So now I'm using 3-layer 256, which are about 10 times fewer weights. And these take about 0.4 milliseconds to sample. I can have about 10 of these per scene. The larger network produces a nicer results. It definitely has a better looking gait and feels more natural, but they're a lot more expensive. So one strategy for making the smaller models work better is to make them more specialized. So you can have separate models for walking and running. Currently, I just have one model that does both and walk backwards. So I could separate those, and then the models could become more specialized. I have done this a little bit, but at the moment, I'm not doing it because wrangling all these different models and training them is a lot of overhead. Once I'm not refining the models as much, I might you start using that strategy to get better looking and feeling movements. Okay, so how do we train these? So the powered Ragdoll characters are agents. These are placed in an environment, and then the trainer collects thousands of episodes from these agents. Episodes are essentially an experience. A single episode is a single Ragdoll character trying to accomplish its task once. For example, trying to walk a little bit. They get terminated after a certain length of time, but if they fail, like fall down or are doing a terrible job of their goals, then I might terminate them early. Now, a reward is computed for each step, and these are added together to come up with a reward for the episode. So the trainer creates batches of thousands of these experiences or episodes, and then it looks at those and uses them to adjust the weights of the neural net in the direction that increases the reward the most. And this iterates this process approximately, in my case, 1,000,000 times. And at the end of that, which takes about 24 hours, you get a trained model. So in my case, as I mentioned, I've got 4 models. And this takes about 24 hours on a fairly powerful gaming laptop to do this training. I'm using PPO reinforcement learning. So I'm not going to explain what that is right now because you can find it on the internet. Better explanations than I can do. The main reward is to mimic animations while accomplishing goals and not falling down. So I'm going to talk a lot about rewards because this is really where most of the effort has gone in the project. They often produce unexpected results. You can see on the left, this was a rewarding jump for long hang time. As you can see, the agent figured out if it didn't put its feet down, it lasted longer in the air. And on the right is a troll, and I was trying to get it to avoid touching the ground with its stepping foot by punishing it if the stepping foot touched the ground. And this is the solution it came up with to minimize the amount of time its feet were touching the ground, which was not what I was looking for. So here we have a little more detail on the reward. So reward is for a single episode is a number between -1 and 1. 1 is usually means you're doing great. -1 is obviously very bad. So the initial stage of training, it's learning to mimic reference animations. I do that by measuring the angular difference between the Ragdoll limb rotations and an animated character limb rotations, take the sum squared of those errors, and then I stuff that into this function. Oops. The intimidating looking exponential function to get a number between 0 and 1. If you look at the graph below, you can see what that number does. So no matter how arbitrarily large the error is, it always maps between 0 and 1. And the larger the error, the smaller that number is. And if the error is 0, it returns 1. And the nice thing about that curve is it has a slope that the trainer can use to always try to reduce the error. Okay, what do we got here? I also have a reward for the goals, which is the difference between the desired speed, desired heading, desired velocity, and the physical speed, heading, and velocity. There's a few other reward terms in there, like feet not skidding on the ground, touching the ground at the right times. Then essentially you multiply all these rewards together to get the final reward. I'm using a little bit of weighting in that multiplying. Now up on the left here, you can see this is all of the reference animations that I'm using overlaid on top of the walking model. So I use that to decide which reference so I actually, and sometimes I score all of the possible animated poses against the current pose. Okay, later on in the training, there's less weight on imitation and a lot more weight on the goals. And I do a few other things, like for the get up, I want it to be as fast as possible. To do this, I add a small negative reward every single step. These accumulate, so the model learns to get up as fast as it can to stop the this negative reward from accumulating. And then actions like get up and jump need to end in a state that can transition to a walk. So to do this, I'll train the get up, and then as the get up is reaching the end of its action, I'll start sampling the walk reward and integrating that into the get up's reward. So the get up learns to get its best reward, it has to get into a pose that the walk model likes. And then when training walk, I often use the get up and jump to generate start poses for the walk. So this helps learn transitions between the models. So as for setup, early on, I sample from the reference poses. So the model starts in a pose that is part of what it's trying to accomplish. Later on, I feed in random poses from other training clips so that the model learns to whatever pose it's in, like for example, the walk model, whatever pose it's in, it can learn to get from there to a walk and recover from a very strange pose. That's important. Otherwise, the models are fragile. If they get out of their known poses, they don't know what to do and they just flail. As training proceeds, the environments get harder, the ground gets rougher, the ground starts to move, harder start poses, and then I start using other models to create start poses when I'm training different models. I use a lot of early termination. This really speeds up training. So you can really punish a model by terminating it so it stops accumulating rewards early if it fails or starts doing badly. You don't want to let it lie on the ground and just flail accumulating reward. So it's good to terminate those as soon as they happen. It really does speed up training a lot, especially for mimicking animations. Early on, I'm pretty ruthless with that. I only let it at the beginning get about 8 frames in, typically before terminating, and it learns quite quickly to get more reward. It needs to not get terminated, so learn to imitate. So once the models have been trained, how do you decide which model to use? This is actually a really tough problem. If you look at this guy running around, should I, like right there, am I falling? Am I tumbling? What state am I in? So you can do all sorts of analysis with fancy math on the positions and rotations and the velocities of everything and try to figure out what's going on. But luckily, there's a magic way with machine learning of getting past this or solving this, which is the models during the training process have a way of estimating what their reward will be, of an estimate of their reward. This is called the value function, and it's a separate model that is a byproduct of the training process. So we can actually use this in the game to give us a score of what is the reward from the current pose of our walk? What is the reward from the current pose of our tumble? What is the reward from the current pose of our get up? And then we can look at which one is producing a good score and go with that model. So it solves a very hard problem for us of deciding which model we should be using. A little bit about my ragdolls. So I've got two ragdolls that I'm doing a lot of work with. One is this giant troll character. It's 30 meters tall, weighs 1,500 kilograms. That one I sample at only 7 hertz, or about 10 times per frame. The main character, or 10 times per second. The main character is just a 2 meter tall character, weighs about 32 kilograms. I'm using physics configurable joints for everything. Obviously the positions are locked. I'm using slurp rotations instead of the Euler rotations. And this model gets sampled at 20 hertz. So to really talk about the results, they're in general pretty good. The character is quite usable. I'm, always tinkering at improving it and making it, trying to get it into a state that's usable in a game. At the moment, that's consisted of making the model smaller, and now I'm trying to get the quality of the movement better. It solves the problem of a lot of actions that are very hard to fake using hacked kind of physics tricks. Also, there's a lot of emergent behavior that comes from using a physically simulated character that just would require a colossal amount of programming to make a non-physically simulated character react these ways. Another interesting byproduct is states like stumbling or dazed or drunk or wounded. A lot of games have states like that for your character, but implementing those literally requires a whole second set of animations. It doubles the work of implementing your character. But with machine learning, you actually can just degrade the quality of your observations, or maybe extend the sample time a little bit. And your model will naturally start staggering and struggling to do whatever task it is. So phenomena like that you can get for free. And then another interesting phenomena is moving uneven terrain, like this guy staggering around on this platform. Getting this sort of movement from an animated character requires an incredible amount of animation and inverse kinematics and analysis to try to figure out how to move the character. But the machine learning models, you get this for free. So that's the good. So the bad, well, this process of creating these models is extremely time consuming, and tuning the result is incredibly time consuming. See, with normal way of doing things, you can just type in a different speed number if your character is not moving fast enough. If your machine learning model is not moving as fast as you want, you have to somehow make it run faster by figuring out a better reward or observations or and then retraining, going through a whole retraining. So tuning these results can take an incredibly long time. Another thing is these wobbly limbs are hard to get rid of. You can see in this character how the main body really wobbles a lot. And the limbs are wobbly too. I haven't really found a great way of getting rid of that. It may end up just being that this is part of the game and I'm just going to have to live with it. It's hard to predict how long it'll take you to find a solution if there's things that your character is doing that you don't like. It may be not possible. Like, I never did find out how to get my idle to work. Yeah, you may never find solution for some problems. Actions that are hard to accomplish in the real world for a real person are also hard to do in the game world with this character. Whereas with classically animated characters, you can pretty much do whatever you can imagine. Also, these characters are fairly expensive. It's a big performance commitment to include these in your game. Realistically, you're probably going to have fewer than 10 of these active in a scene at a time in a realistic game. At least for physically simulated characters. Other models that are like doing AI or something, if there's small models with small observations, you could have more of those. So that is the result. So I'm going to open this up to questions. I would like to thank Unity ML agents for their support and providing this great work framework. Also, I've been was invited to participate in their cloud training project, which is great. My son thanks them a lot because I'm no longer doing my training on his gaming computer when he's not using it. So big thank you for Unity for that. So I'm going to open this up to questions now.
All right. Thank you so much. Some of the questions, let's see. One of the questions has anything, I know you've come across many different renditions of the locks and everything. Has anything completely surprised you going through this that you just didn't expect was going to happen?
I think what surprised me is actually how well it worked. In some ways, in some ways the models have exceeded my expectations on what would be possible with them. But yeah, every day when I get up and look at what was trained overnight is a bit like Christmas morning. It's like, I'm not sure what I'm going to get. Most of the time, it's not what I'm expecting.
All right, another one of our questions from Clay. It says, what do you need to do to optimize for different platforms?
I haven't tried a lot of platforms. I'm targeting PC, so pretty powerful platforms. I don't think you need to do a lot other than just, before you would start, I would test on the platform to see how big a model it can handle, just how long it takes to execute each model. Yeah, I don't think I will be able to use my physically simulated characters on mobile. I haven't tested it yet, but I'm pretty sure they're not going to be up to the job.
All right. Kenneth asks, so how do you see this eventually playing out for more behaviors like swagger and attitude?
That's a good question. I don't. Some things like moving the head or the arms independently, you can create attitude by using an animated animation on top. So I could put the hands on the hips. I could move, have the head look at things. So I can create some swagger that way. You could use different animations to create a different character. So if you had a beautiful model walking down a catwalk, she would have a very different walk than a football player. So you could use a model on the catwalk animations and football player animations, trains two separate brains, and you could switch between the brains. It would be a lot of work to set that up and do it. So I'm not sure you'd be better off doing that or using like a canned animation.
Another question we have is, where do you see this being applicable to what types of projects? You said it was a very process heavy, and will the types of projects change over time?
To be honest, this is really new technology. I think there's a lot of potential for different things. I have wondered a little bit if people making like machinima type videos might want this just to create a whole bunch of characters that they don't have to animate and control, that just automate for them in a more realistic way. So that's one application. My goal is to create a game that's something like a cross between Shadow of the Colossus and Goat Simulator. That's what I'm trying to do with it, sort of a third-person controller type game. I think games like Gang Beasts are a possibility, sort of local multiplayer or even networked multiplayer with a lot of physics humor in them. One thing about these characters is simple things are often awkward and difficult. But there's a lot of games that have been built around that meme, like Octodad and Surgeon Simulator and QWOP have all really embraced awkward controls and physics awkwardness as really the whole point of the game, and they've been very successful. So those are some of the uses I see for this.
Thank you again. We'd like to thank you and everybody from CSGC for having you come and talk to us. Is there anywhere that if people had more questions where they can contact you?
Yeah, I've got a website, digitalopus.ca. I'll leave it with Professor Arkham about that contact information. So I'm easy to contact. I also am on Twitter and YouTube. I have some video clips, so you can contact me through those.
All right.
Yeah, so that's those would be the best places to contact me.
All right. Yeah, just send me the link and I'll toss it in the chat for everybody.
Okay.
And thank you again.
And I think after this, I'll dump into the chat place for the conference and hang out there for a bit. So if people have questions, they could ask me there.
All right. Sounds great. Thank you.
Okay. Thank you.